Welcome to this documentary. In a flash, these cosmic explosions outshine entire galaxies, then vanish forever. The story of the universe is written in light, but its most powerful sentences are screamed in a language of pure annihilation, in bursts of radiation so fierce they can be seen from the edge of time itself. This is the story of gamma-ray bursts, the universe's grandest and most violent farewells. For billions of years, a massive star has burned in a distant galaxy, a furnace of immense power and stability. It is a cosmic titan, many times heavier than our own sun. Deep in its core, the relentless crush of gravity is balanced by the outward push of nuclear fusion. The star lives a fast and furious life, fusing hydrogen to helium, helium to carbon, and on through the periodic table in a desperate race against its own mass. Each new element provides less energy, burning faster, until the core becomes a forge of iron. Iron is ash. It cannot fuse to release energy. For the star, this is the quiet, inevitable end of the road. The nuclear fire that has sustained it for millions of years winks out. In that moment, silence falls at the heart of the giant. Gravity, patient and undefeated, seizes its chance. With no outward pressure to oppose it, gravity collapses the iron core in less than a second. The core, once larger than Earth, is crushed into a sphere of pure neutrons just a few miles across. The outer layers of the star, suddenly unsupported, begin a catastrophic plunge inward at nearly a quarter the speed of light. They do not fall onto a solid surface, but onto the newly born, impossibly dense neutron star. The impact is unimaginable. It creates a shockwave of such ferocity that it rebounds outward. This is the birth cry of the event. For the most massive stars, the collapse does not stop at a neutron star. The core continues to crush itself into a point of infinite density, a black hole. The infalling matter swirls into a frenzied, superheated disk around this cosmic drain. Now, the universe's most powerful engine roars to life. Along the star's rotation axis, where resistance is lowest, the energy of the collapse finds its escape route. Twin jets of plasma, threaded with magnetic fields and moving at over 99.99% the speed of light, blast their way out through the carcass of the star. They are not made of fire, but of something more fundamental, a soup of particles and radiation accelerated to energies beyond any earthly particle accelerator. These jets are pencils of pure fury, narrower than most people imagine, perhaps only a few degrees wide. If the dying star were a lighthouse, these jets are the beams. You must be looking almost directly down the barrel to see the true spectacle. The jet punches through the star's outer envelope in a matter of seconds. As it breaks into the interstellar void, it collides with material shed by the star in its earlier life. This collision is the trigger. Here, internal shocks within the jet or external shocks with the surrounding material convert that insane kinetic energy into radiation. The process creates a pulse of gamma rays, the most energetic form of light in the universe. This is the burst itself. For a few seconds, or sometimes several minutes, this single object outshines every star in its entire galaxy combined. It releases more energy in those seconds than our sun will in its entire 10 billion year lifetime. All of that energy is focused, beamed, concentrated into those two narrow jets. The power is stupefying, a brief flash that represents the conversion of a star's core into light and fury. The initial flash, the prompt emission, is a storm of gamma rays and hard X-rays. It is a chaotic, spiking signal, each millisecond a testament to the violent turbulence within the jet. This is the event's true peak, its moment of supreme self-expression. But it is not the end of the story. It is merely the opening salvo. The aftermath of that initial explosion unfolds on a longer, grander stage. The jet, now plowing into the tenuous gas of interstellar space, begins to slow. It acts like a cosmic plow, sweeping up material and heating it to incandescence. This creates a long-lived, expanding fireball known as the afterglow. The afterglow is the burst's echo, fading but telling. It radiates across the electromagnetic spectrum, from X-rays down through visible light to radio waves. Astronomers train their telescopes on this fading ember. It is their Rosetta Stone. The afterglow reveals the burst's distance, its host galaxy, and the energy of the explosion. It tells us we are witnessing events from the universe's childhood, bursts that occurred when the cosmos was just a fraction of its current age. We are seeing the deaths of some of the first stars, the beacons that helped end the cosmic dark ages. The afterglow can linger for days, weeks, even months, a slowly dimming testament to the violence that preceded it. But what of the local consequences? Imagine a world orbiting a star a few thousand light-years away, a world with a nascent biosphere. For that world, the burst is not a distant curiosity. One of those lethal jets is pointed directly at it. The first sign is not light, but a silent rain of gamma rays and cosmic particles arriving at the speed of light. The sky, for a moment, flashes with an invisible, deadly brilliance. The gamma rays rip through the atmosphere, smashing apart nitrogen and oxygen molecules. They initiate a chemical cascade, breaking the bonds of life and forging new, poisonous ones. Nitrogen is fused into nitrogen oxides. These compounds ravage the ozone layer, the planet's shield against ultraviolet radiation. Within days, the ozone is gutted. The planet's surface and its oceans are now bathed in the full, sterilizing fury of its sun's ultraviolet light. Photosynthetic organisms die en masse, collapsing the base of the food web. The nitrogen oxides fall as corrosive acid rain. A faint, ghostly afterglow might be visible in the night sky for a few weeks, a beautiful and deadly reminder. For that world, it is an extinction-level event from the depths of space, a reset button pressed by a star's death millions of years earlier. Some scientists look at Earth's own fossil record, at the Ordovician extinction over 400 million years ago, and wonder if a distant gamma-ray burst, a shot from a cosmic gun we never saw, could have been the cause. The story of a gamma-ray burst is the story of transformation. It is the death of a star, the birth of a black hole or a magnetar, and the creation of a beacon that cuts across cosmic time. It is a forge for heavy elements, scattering iron, gold, and uranium into the galactic environment. These events are rare in any one galaxy, happening perhaps once every 100,000 years, but the universe is vast, and so we see them daily, flickers from across the abyss. Each flash is a final, brilliant chapter in the life of a cosmic giant, a reminder that even in the vacuum of space, nothing truly dies quietly. It screams its ending in a language of pure energy, a brief, blazing testament to the fact that the universe is not only stranger than we imagine, but infinitely more violent and magnificent. The afterglow, that fading fingerprint on the sky, is more than just a slow fade to black. It is a dynamic and complex phenomenon, a laboratory of relativistic physics unfolding in real time. As the jet continues to plow outward, it does not move into a perfect vacuum. The interstellar medium is a patchwork of clouds and voids, and the jet itself is not a smooth bullet but a turbulent, clumpy flow. This leads to a light curve, the graph of its brightness over time, that is not a simple, smooth decline. It is a story written in dips and plateaus, in sudden rebrightenings and sharp decays. Days after the initial cataclysm, as optical and radio telescopes remain locked onto the fading point of light, a new feature might emerge. A supernova. Not just any supernova, but a superluminous one, its light finally catching up to and sometimes even overwhelming the afterglow. This is the final, explosive death throes of the star's outer layers, the part not consumed by the jet or the black hole, now blasted outward by the neutrinos pouring from the collapsed core. It is the star's funeral shroud, billowing out to reveal the newly forged elements in its spectrum: cobalt, nickel, titanium, and gold. The supernova confirms the progenitor, a massive, rapidly spinning star, likely stripped of its outer hydrogen envelope, a Wolf-Rayet star meeting its spectacular end. For astronomers, catching this supernova signature is the crucial link, the smoking gun that connects the theoretical model to the brilliant, observed reality. But the engine at the heart of the chaos is not always finished. In some cases, the newborn compact object is not a quiet black hole, but a magnetar, a neutron star born spinning hundreds of times per second and possessed of a magnetic field a quadrillion times stronger than Earth's. This object is a powerhouse in its own right. Its furious rotation and decaying magnetic field can inject energy into the expanding blast wave for hours or even days. This continuous energy input can cause the afterglow to plateau, to remain stubbornly bright long after it should have faded, as if the universe is reluctant to let the curtain fall. The light curve becomes a biography of the central engine's activity, a sign that something is still violently alive within the wreckage. Meanwhile, on that hypothetical, unlucky world in the jet's path, the catastrophe deepens. The initial gamma-ray pulse, lasting perhaps 30 seconds, has passed. The sky appears normal to biological eyes, but it is now a toxic, altered thing. The chemical cascade in the upper atmosphere is complete. The ozone layer, which took eons to build, is now a tattered ruin. As the planet rotates, every inch of its surface is exposed to the full, unfiltered ultraviolet radiation from its sun. In the oceans, the phytoplankton, the microscopic engines that produce most of the planet's oxygen and form the foundation of the marine food web, begin to die. Their DNA, shredded by the UV, ceases to function. Blooms of life turn into vast, sinking mats of grey organic sludge. On land, the same devastation unfolds. Plants wither, their leaves burning and their photosynthetic machinery destroyed. Herbivores starve. Carnivores find their prey vanishing. The nitrogen oxides, created in the high atmosphere, now descend. They mix with water vapor to form a pervasive, corrosive nitric acid rain. It is not a dramatic downpour, but a persistent, acidic mist that falls for months, leaching nutrients from the soil and poisoning freshwater lakes and rivers. The pH of the surface ocean plummets. For any shell-building creatures, this is a death sentence. Their calcium carbonate structures dissolve in the newly acidic waters. Yet, even in this global sterilizing event, niches might persist. In the deep ocean, near hydrothermal vents where life is powered by chemosynthesis rather than sunlight, ecosystems could remain untouched. In caves, or deep underground, organisms shielded from the radiation and the acid rain might survive. The extinction is profound, but it may not be total. The planet's biosphere is reset, not erased. The evolutionary clock is wound back, and the stage is set for a long, slow recovery, driven by the hardy survivors. This is the grim lesson of the gamma-ray burst. It is a directional apocalypse. It does not shatter planets or strip away atmospheres, it surgically removes the conditions for complex, surface-dwelling life, a silent, invisible scourge from the depths of the galaxy. Back in the realm of observation, the study of the afterglow enters a new phase, the radio ring. Weeks to months after the burst, as the expanding shockwave becomes truly enormous, light-years across, it begins to resolve in the most sensitive radio telescopes. It is no longer a point source, but a faint, growing ring. By monitoring the size and expansion speed of this radio remnant, astronomers can perform a fundamental check on their models. They can measure the true energy of the explosion independently, confirming the mind-boggling calculations made from the initial flash. This radio echo can persist for years, a final, whisper-thin signature of the event merging with the general radio haze of the host galaxy. And the host galaxies themselves are a subject of intense study. They are often small, irregular, metal-poor galaxies, cosmic building blocks from the early universe, or their modern-day analogues. These are places where massive, primitive stars can still form and die quickly, without the enriching pollution of many previous generations of stars. This environment is crucial for producing the kind of fast-spinning, massive progenitor star needed for the engine to work. Finding a gamma-ray burst in a large, spiral galaxy like our Milky Way is exceedingly rare. Our galaxy is too settled, too chemically mature. The bursts prefer the cosmic frontier. The legacy of the burst extends far beyond light. The jets are accelerators of cosmic rays, flinging protons and atomic nuclei to energies that dwarf anything produced in our most powerful colliders. Weeks after the initial flash, as the relativistic afterglow from the jet fades by another factor of 1,000, the light from this supernova begins to dominate. We may be constantly, faintly showered by the distant, decayed remains of these stellar cataclysms. Furthermore, the violent nucleosynthesis in the jet and the associated supernova is a primary candidate for the creation of the heaviest elements in the universe, like gold, platinum, and uranium. The rapid neutron capture process, or R process, requires an environment of insane neutron density and high temperature, conditions thought to exist in the turbulent wake of a merging neutron star or in the winds from a magnetopowered burst. Each brilliant flash may be seeding future generations of stars and planets with the atoms that will one day form continents, computer chips, and living cells. The burst is not just an end, it is a dispersal, a sowing of the seeds for future complexity. Finally, as the last whisper of the afterglow fades from the most sensitive radio telescopes, years or decades later, what remains? At the heart of it all, a new compact object, a black hole, perhaps now slightly heavier from the accreted stellar material, or a rapidly spinning magnetar that will gradually slow its magnetic field decaying over millennia. The surrounding interstellar medium is forever changed, enriched with heavy elements and stirred by the shock. The event becomes a footnote in the history of its galaxy, a transient spike in its overall light output that would be virtually undetectable in its integrated spectrum just a century later. Yet, the information, the story of that violent transformation, continues to travel. The flash of gamma rays, the afterglow, the supernova light, all of it races outward at the speed of light, a spherical shell of information expanding into the cosmos. For any other civilization, on a planet in a galaxy millions of light years away, that event has not happened yet. They will see it in their future. Our detection of it is a glimpse into their distant past. In this way, gamma-ray bursts are stitches in the fabric of space-time, linking different epochs and different locations in a web of cause and effect written in radiation. They are the universe's most dramatic punctuation marks, exclamation points of annihilation that, in their dying light, illuminate the laws of physics, the life cycle of stars, and the fragile nature of life itself in a cosmos capable of such breathtaking violence. The scream fades, but its echo, in data, in theory, and in the newly forged atoms drifting through the void, shapes the universe forever. The story, however, does not end with the fading of the last radio whisper. The narrative of the burst splinters into 1,000 threads, each tracing a different consequence through time and space. On the unlucky, irradiated world, the acid rain finally ceases. The sky, once a lethal window, begins a slow, chemical healing. The nitrogen oxides, having done their damage, gradually break down or are washed from the atmosphere. But the ozone layer is not so easily rebuilt. It will take millennia for natural processes to restore that critical shield. In the interim, the surface remains a desert scoured by ultraviolet light. Yet, in the perpetual darkness of the deep ocean trenches, around vents spewing mineral-rich, superheated water, life not only persists, it thrives. These ecosystems, based on sulfur-oxidizing bacteria and the strange, armored creatures that feed on them, are utterly oblivious to the catastrophe above. They have existed in their own timeless, sunless world for eons, and the gamma-ray burst is less than a rumor here. Artists create stunning, haunting images of the black crust ecosystems and the deep-sea vent kingdoms, extrapolating from the scant data. A celebrated symphony is composed, its first movement a serene, deep cello piece representing the ancient vent life, interrupted by a terrifying, percussive flash movement, using sudden, full orchestra strikes and a chorus singing shifted white noise, followed by a slow, atonal, yet strangely hopeful third movement built on repeating, minimalist patterns, the rebirth. The burst becomes a benchmark for human timescales. Historians start referring to the pre-GRB and post-GRB eras in long-term astropolitical forecasts. In the dwarf galaxy, the supernova remnant continues its beautiful decay. The cosmic flower has now begun to fragment. Rayleigh-Taylor instabilities, where a lighter fluid pushes against a heavier one, have created delicate, finger-like structures in the expanding shell, making it resemble a dandelion head ready to disperse. The black hole, its appetite sated, is now a dormant pit. But its first dynamical effects are being felt. A binary star system, passing within a light year, has had its orbit noticeably altered. The two stars, once tightly bound, are now on wider, more elliptical paths around each other, a telltale sign of a massive, unseen perturber. Astronomers tracking this system add one more data point to the map of the black hole's invisible kingdom. The enriched cloud, the nebula of creation, is now encountering the first ripples of the predicted shockwave from the neighboring cluster supernova. The compression is not uniform. It creates a lacework of denser filaments within the cloud. In the computer models, these filaments are where the next generation of stars will be born. The models zoom in on one filament, rich in iron-60 and aluminum-26 isotopes, the unmistakable radioactive clocks of recent supernova nucleosynthesis. This filament is destined to fragment into a small stellar nursery. The simulation highlights one particular knot of gas and dust. Its composition is exceptional. It has a higher-than-average concentration of platinum group elements and, intriguingly, a distinct isotopic ratio of carbon that matches models of hypernova ejecta, the fingerprint of GRB 230919A. This knot, the models suggest, will form a star of modest size, perhaps a G-type star like the Sun, with a robust protoplanetary disk. And the light sphere, the eternal traveler, continues its journey through the expanding dark. It has now been redshifted so that its peak emission is in the microwave band, blending with the cosmic microwave background, but its unique temporal signature, the rapid rise, the complex multi-wavelength afterglow, remains detectable as a slight anisotropy, a tiny bump in the perfect thermal curve of the early universe, for any civilization advanced enough to build a sensitive enough all-sky map. It is becoming one with the fossil radiation of the cosmos, its specific story dissolving into the general hum of creation. Yet, the story is not one of dissolution, but of transformation and relay. The energy of a dying star, focused into a beam of pure destruction, has become a catalyst across unthinkable scales. It forced a biosphere to reinvent itself in a more hardened image. It sharpened the mind of a distant, watching species, pushing it to think of survival in galactic terms. It enriched a cloud with the seeds of planets and, perhaps, life. And its final, faded photon might have provided the quantum of energy needed for a critical step on a world it will never know. The narrative that began in the stardust of a collapsing core does not end, it branches, it adapts, it weaves itself into the fabric of everything that follows. It is a story written in fire, but its chapters are inscribed in the genetic code of radiation-hardened microbes, in the design documents of planetary defense projects, in the isotopic anomalies of newborn star systems, and in the faint, microwave whisper of the cosmic background, a testament to the fact that in the universe, an ending is always, and only, a new kind of beginning. The story, then, is one of parallel evolutions, of life and consciousness and matter all responding to the same ancient, fading signal. On the irradiated world, the knobby pillars of symbiosis spread across the high plateaus. They are not yet organisms, but rather ecosystems in miniature, stable, self-sustaining accretions. The photosynthetic partner, over millennia, evolves a pigment more efficient at capturing the dim, redshifted sunlight, a deep burgundy that stains the towers a rusty umber. The radioactive archaea at their core, sustained by the planet's inner warmth, act as a constant geothermal battery, allowing the structure to survive the long, global nights that still grip the world. Condensation from the thick atmosphere collects in the matrix's pores, creating internal, mineral-rich aquifers. Here, other microbes find refuge, silicate-shelled consumers, iron-sulfur metabolizers, and a new, motile form that can navigate the microscopic waterways, grazing on biofilms. The tower becomes a city-state. A tectonic shift changes everything. A massive quake along a continental rift causes a plateau to tilt. A forest of these towers, undercut by the movement, collapses into a newly formed, deep basin. The rubble forms a vast, porous mound at the bottom of what quickly fills with water to become a sea. Submerged, the photosynthetic components of most towers die, but the radioactive archaea, now buried in a wet, anoxic environment, thrive. Their constant, low-grade heat warms the mound from within. Hydrothermal circulation begins, drawing in cold seawater through the lower rubble, heating it, and venting it from the top of the mound. It becomes a giant, diffuse, biological vent system. In this new, stable, and energy-rich environment, a breakthrough occurs. A motile microbe, one that had evolved to shuttle electrons between sulfur and iron compounds, finds itself in the gradient-rich zones of the warm seep. It develops a primitive, lipid-based membrane that can maintain an electrochemical potential. It learns not just to facilitate reactions, but to store the energy difference in a molecular currency, a clumsy, inefficient precursor to ATP. This is the birth of true cellular metabolism, independent of direct chemical consumption. These protocytes begin to colonize the entire warm mound. They diversify, some specialize in harvesting energy from the heat-driven sulfur gradients, others in breaking down the complex organics leaching from the decaying tower matter. Competition returns, fiercer now, driven by a new imperative: efficiency of energy capture and use. Meanwhile, in the human realm, Project Umbra faces its first practical test, not from a GRB, but from its own ambition. A prototype orbital manufactory, designed to convert asteroidal material into vast, thin sheets of radiation-reflective foil, suffers a cascading software failure during a solar sail deployment test. Instead of a single, coherent sheet, it spews a cloud of glittering, uncontrolled debris into a high Earth orbit. The cleanup effort takes years and costs billions, sparking a fierce political and philosophical debate. The cosmic realists argue this is the necessary cost of learning to build big for survival. A new faction, the Terran Stewards, gains traction, arguing that such grandiose cosmic engineering is a dangerous distraction, and that humanity's focus should be on perfecting planetary biosphere management and the arc vaults. The debate stalls major funding decisions for a decade, but in the engineering labs, the work continues quietly, learning from the failure. The next-generation designs are modular, redundant, and include passive safe mode protocols. The cultural absorption of the event deepens. The GRB becomes a religious touchstone for some. A neo-Gnostic sector rises, preaching that the burst was a divine pruning, a necessary destruction of a flawed material realm to make way for a purer, harder, more conscious existence, mirroring their own world's technological hardening. Their rituals involve periods of sensory deprivation in simulated radiation shelters, seeking a flash of clarity. Conversely, a school of deep ecology points to the sterilized world's resilient microbes as a model for a non-anthropocentric, post-apocalyptic ethic of life. Their influence is seen in the design of the arc vaults, which are increasingly envisioned not as human-centric bunkers, but as life arcs, preserving entire microbial and invertebrate ecosystems deemed most resilient to radiation. In the enriched nebula, the shockwave from the neighboring supernova has fully engulfed the filament. The compression triggers gravitational collapse in a dozen dense knots. Among them is the special knot, the one bearing the isotopic signature of GRB 230919A. As it collapses, conservation of angular momentum spins it into a disk. At the center, a protostar flickers to life, its growth fed by the infalling, metal-rich gas. The radioactive isotopes within it, the aluminum-26 and iron-60, heat the inner disk from within, driving a vigorous thermal and chemical activity. The platinum group elements, having a high condensation temperature, are among the first to solidify out of the cooling gas as microscopic nuggets. They become the nucleation points for the first dust grains, which are unusually heavy and metallic. Within this protoplanetary disk, the story of the burst is written in stone and metal. The early-forming planetesimals that coalesce close to the young star are incredibly dense, rich in tungsten, platinum, and iridium. Farther out, where water ice can survive, the isotopic anomaly in the carbon creates organic molecules with a slight but distinct chemical handedness, a subtle bias that may, billions of years later, influence the chirality of biology on any world that forms there. The system is being seeded, preloaded with the refined products of stellar catastrophe. The light sphere itself, now a whisper in the microwave, encounters a region of space not empty, but filled with the tenuous plasma of an ancient galactic wind. The interaction is immeasurably faint, but it imparts a minuscule, additional polarization to the microwave photons, twisting their orientation in a pattern that encodes the direction of the burst's original jet. This information, hidden within the cosmic background, is a message in a bottle so vast and diluted it may never be read. Yet, it persists. Back on the irradiated world, in the warm, chemical-rich darkness of the submerged mound, a chance encounter changes the course of evolution. Two different lineages of protocytes, a sulfur gradient energy harvester and an organic matter consumer, become physically entangled in a biofilm. Through a series of faulty divisions and failed consumptions, they end up not destroying each other, but cohabiting within a shared, toughened membrane vesicle. The harvester provides a steady, internal trickle of chemical energy. The consumer, now internalized, breaks down complex molecules from the environment, providing raw materials. This endosymbiotic event creates the first true composite cell, an organism with internal compartments dedicated to specific functions. It is wildly inefficient and unstable at first, but it possesses a monumental advantage: it can actively manage its energy budget. This cell is the ancestor of all complex life on this world. Its descendants will eventually develop ways to harness light again, not through loose symbiosis on a tower, but with dedicated internal organelles, reclaiming the surface from a new, more sophisticated, and deeply resilient foundation. The narrative thread, now woven into the substrate of a cell, the policy of a species, and the composition of a protoplanetary disk, continues to unwind. The energy from the burst, transformed and delegated across time and space, is no longer a story of a single event, but the foundational hum underlying a multitude of new beginnings. The universe does not forget, it repurposes. And in the silent, patient chemistry of a warm, dark mound on a scarred world, and in the stubborn, fearful hope buried deep in the rock of another, the repurposing takes on a shape that, against all cosmic odds, begins to understand itself. Thank you for watching. If you enjoyed this documentary, please like and subscribe for more stories every week.